Thanks. So we'll be talking about the Zinc today, and kind of to give the recap of previously in Scala 2017, when I was talking about SPT1, I was thinking about basically splitting the code base of SPT into a bunch of modules, and one of them was Zinc, and the other is Library Dependency API. And here I'm using sort of like a skateboard as a metaphor, where you can basically use like trucks and wheels and board, and you can exchange them. And this is kind of like a way of making sure that the individual components can essentially be upgraded without basically completely breaking the build ecosystem. And recently we released SPT 1.3 that swapped the library dependencies implementation from Apache Ivy to Corsair, basically using this API as a mechanism to buffer these two different things. So here, I want to talk about the second one that's mentioned, which is the Zinc API, and kind of like go through the overview of what's incremental compilation, and from there, what we can learn and what we can potentially improve. So before we talk about the incremental compilation, I think it would be kind of like useful to mention the separate compilation, because it's something that kind of happens, but it's a feature sort of a compiler that we're not really always aware of. So what's separate compilation is basically you have a.scala, right, that generates a.class. That's the first compilation. And after you do the compilation, you can actually invoke Scala compiler to compile b.scala. That's referencing a.class. This seems kind of like, of course, intuitive, but it is actually a feature that is allowing you to do that. And more general sort of case, or different variety of case, is if there's a library like a.scala and a bunch of other files that generates a.jar, and then your application can refer to the jar, b.scala, putting a.jar into the class path. So in the talks, like in the contributor summit, the reactive Scala came up several times, and it's like one of the quotes in there that I wish someone told me when I was starting out with Scala is that in Scala, specifically, I think, types are a property of expressions, and thus it only exists during the compile time. So because of the erasures, right, like if you think about like the sequence and things like that, like some stuff might be retained during the runtime, but mostly a lot of the things that we think is types exist when you're doing a compilation, right? And if you actually look into the bytecode, a lot of these type informations are gone. So how are we actually able to do the separate compilation? Is that sort of like secretly inside of the a.class, basically representing Java runtime code, there's a signature information called pickles. So that information basically is a Scala-specific type of information that's persisted together with your class, which allows the compiler to read it during the compile time in order for you to be able to do the separate compilation. So kind of like, let's look at like specific cases where, let's say b.scala here is calling some a.something from a.scala, right? If you look at this, there's this thing called JavaP. If you go to the console and type colon JavaP example B, you can actually see like bytecode of what Scala compiler generates. And this is like a useful tool / technique that people can just go home and try. And in there, basically, there is the point at which I'm calling new.a, and that's invoke special 15. 15 just basically is some like number that the compiler assigned for that name in it and stuff. So the number doesn't really matter. What matters is the invoke special part. And a.something is represented as invoke virtual. So The actual specific code doesn't matter, but the point is that in order for you to compile something, at the Java bytecode level, it's almost like you're writing like Python or C or something like that. There is no real information of the type. You just need to know the name of the function, basically, that you're calling. And then the linking happens sort of like on the fly. And this is kind of like a base, like a mechanism that allows you to be able to compile things separately. So what is incremental recompilation or compilation, right? And it kind of comes down to this concept called minimality. And there is a paper called Build System a la carte that defines type system, or I mean the build system, to be a minimal if it executes a task only once during the build, and only if its input has transitively changed, basically, right? So we can kind of substitute what I said in terms of the compilation. You can think of it as it compiles source at most once per build if they transitively depend on sources that changed since the previous build. Right, that's basically sort of like how you can check what it means for something to be incremental. So the naive approach to the incremental recompilation is kind of how like people would imagine the incremental compilation to happen, is that first, when you do the first round of compilation, you have like a.scala, b.scala, and a whole bunch of other stuff that depends on, b.scala, right? So you track this information kind of like as a dependency relationship. And then the second step is, well, let's say you type something into a.scala, then you do this initial invalidation looking at like timestamp or hash or something like that, right? Then you flip the arrow backwards to look at what is a transitive invalidation. So what's the problem here is that, as you can kind of imagine like how source works, like once in this particular case, the graph looks almost simple, but in reality, it's like a web of the networks that each refer to other things. So in a large code bases, like what Lori was talking about previously, this can basically spread like wildfire, right? It's like you change one source, now you have to compile like 50% or 70% of your stuff. At that point, it's actually much more probably efficient to not do the incremental compilation and just do the full compilation. So in order to sort of like work around this situation, Zinc, since 0.13, used this optimization technique called name hashing. And it's kind of fun to talk about name hashing in this conference because it was created by Grzegorz-Kosakowski in 2013. And it has been basically the default incremental in, like I said, 0.13.1. And for SBT1 Zinc 1, he also updated it so that it's tracking the name hashing in a more granular way. So the goal, like I said, is we need to prevent this concept of invalidation from spreading downward unnecessarily, right? So how do we do this? So first, there is two types of source dependencies now. First, you can think of it as kind of like a stronger dependency, is the inheritance. This is basically like your class inherits something else, like interface or traits, right? So this is a stronger relationship we have. And the other stuff, basically, we call it member ref inside of the code, but just any sort of like a reference. You're calling method, a bunch of like invoke virtuals, basically. You're just referring to some sort of type name or term names. And these are kind of like a weaker relationship. So step two, when we do the compilation, there's sort of like an additional step that we do now that we're going to start to track your method signatures and some other information, which we'll get back to. And then normally, like the same thing as the initial validation, you type your code. Then the Zinc would look at the timestamp or some other build tool might use hash to come up with the initial invalidation. For inheritance, there's really no way of like working around this stuff to just compile, right? Because you need to do a lot of checking for the inheritance. So for this is like the situation hasn't changed. If your C3.scala inherits something inside of the B.scala, we would actually do the recompilation here. What's interesting is that now that when we did the initial the invalidation, you can compare the API, like list of signatures from the previous one, and then track exactly what method was changed, or what was removed, or what was added. And then we can invalidate only if the usename is affected. What does usename mean, right? So in here, like we looked at a dot something, the usename looks like this. So during the compilation, Zinc is actually tracking all the names. And it's kind of like at the a level of just basically these like a symbol names. And inside, you see all the way in the bottom something there, right? So if we added, for example, some other, like if you, let's say, in this case, you changed the implementation or something like that, this doesn't really matter, right? Like you remember the whole, like the Wingo virtual thing, the content of your body almost doesn't matter from the point of view of compiling B itself. You just need to basically call it, right? So maybe I can just demo this part a little bit. So hopefully everyone can see this part. Yeah, right. So all right, let's just start with clean first to make sure. And can everyone see in the back? Okay, cool. So just switch this first compilation. This is compiling 3 sources, right? Now, oops. We'll change something to return 1. Was it 1? Is it 0? Let's just use 2. All right. So here, it compiled only 1 source, right? It says compiling 1 Scala source, which means that there is B.scala here that's calling a dot something, but B wasn't triggered here. The other situation is, let's say you say something else. Same thing, right? So it's compiling only 1. And just to kind of check, let's just change the return type of this to double. And now it compiled 2 of these. Maybe just to check what I was saying earlier, we can also check the inheritance cases, right? So here we have foo, and then let's say C extends B. So in this case, let's add a bar and 0 or something like that. So this should, yeah, this forced the compilation on C, right? Because it has a stronger relationship. Yeah, so body change doesn't matter. Also, unused names, it doesn't matter either, right? We added something else. So to recap again of what name hashing is doing, it prevents the invalidation from basically spreading like wildfire. And kind of like, I want to also discuss the nature of the Zinc as sort of like a software or project. And this is a technique we're using called compiler bridge. What's interesting about like Zinc or SBT in general is that it was kind of created almost as an afterthought by someone else, like Mark Hara, after compiler was released, right? Like he was like a physics grad student who was frustrated with like full compilation, so he just added this thing afterwards. So how is it doing this? Is that the basically Zinc is almost like the delivery mechanisms for the compiler plugin. And what we do is that it's able, so Zinc gets released, you know, like let's say like every like year or so or something. And then Scala also gets released in every few years. But sometimes we're able to compile stuff that is released into the future, right? Like 2.13 got released after Zinc 1 was released, and it's still able to do like the 1.28 or something, is able to compile something from the future. This is possible because it's actually using the sort of like a source compilation here. Out in the internet, there is compiler bridge source files, basically published into the Maven Central. And Zinc downloads that stuff when I notice that, oh, I've never seen this Scala version before. And it compiles that stuff against compiler interface, which is basically Java interfaces. And then on the fly, we inject that stuff, like basically a compiler plugin, like I said. And that's how it's able to do incremental compilation. And these are kind of phases. API extractor, like I said, we need to extract these APIs. These are signature information, and dependency tracks these relationships. The analyzer at the end, it's not really doing anything analyze like cool. It's just looking at what class files that was generated from the source. In terms of the timing, this is looking at the really large source code base that the Lori also was looking at, and kind of give you the idea of how like the breakdown of these phases looks like. Typer basically takes up 50%. So this could be like if your entire build is like 30 minutes or something, 15 minutes is pretty much spent doing typing. And the red part is the API extraction. The yellow is the dependency. Then there's whole other stuff that happens in the middle. The middle part basically gradually simplifies your Scala code to make it more and more look like Java. And all the way at the end, JVM, that's basically emitting the bytecode. And there's tiny, tiny sliver at the end for an analysis phase, but that's almost like 0%. You're not going to really see this in this graph. And inside of the Zinc, there is a concept sort of like a dependency origins. I was like reading the Zinc code to figure out like, you know, what can we kind of like track as sort of like a dependency between like projects and stuff like that. And basically there's 3 different origins inside of the Zinc code. There's different categories of things. First is basically your like a local thing, right? Like your one sub-project and you have a bunch of code. And for local, you have full information, so you can do regular like incremental compilation, as you can imagine. Other kind of interesting thing is the sub-project. Because we have the analysis information, you can do basically incremental compilation for the sub-projects. And for the library jars, we don't have that information. So we can't do these checks like, did your API change? Am I using your name? So there is kind of like a difference between what origins these like symbols come from that we're able to do certain level of the incremental compilation. The other kind of interesting aspect that Lori also touched on is that for sub-projects, we just pretty much need the signature information in order for us to be able to do the incremental compilation, right? It's from the upstream. So here are some of the next steps. And these are kind of like a mixture of different ideas. And I'm not going to take credit for all these ideas because some of them are already worked on by others, my colleagues, or people have been doing it for like many years. So here are sort of like a next step towards what we can do, like sort of almost as like ecosystem. Is I think one of the goals we should try is liberation from a machine. And what does that mean? If you look into the analysis file in Zinc, it looks kind of like this. There's a whole bunch of information about your particular machine information, mostly in the form of absolute path, right? This is really, really inefficient because this is stuff that we're saving every time you call compile, like regardless of how you're invoking compilation, because that's how Zinc thinks in, is Java IO file. We don't have to be stuck here, I think. We can think in terms of the virtual file. Basically, you need some notion of a.scala and feed Scala the content of the source, right? And there has been like multiple attempts at lifting this information afterwards. Like Krzysztof, for example, have Hoarder, right? And also like I think Foursquares and all these other people have tried mapping this information out of analysis. But we don't have to map things if we just didn't track things inside anyways. And I think that would have really good memory implications by just saving that space, right? Because this gets pretty large. And also, I think the compiler, should be able to handle these things better. The other part is, like, for example, here you see RT jars, right? So it's not just the source files, but also the libraries. We shouldn't have to know the exact location of your Corsair cache. And by lifting this information, you gain some freedom. The other is liberation from time. Like inside of Zinc, here we see last modified, right? That's kind of like weird because like, why does it matter like what time you woke up last night and typed compile? Should that affect the jar? It should never, right? Like that information needs to be lifted out, basically, so that you can actually do other things. And what other things we want to basically eventually reach towards is the repeatable build, right? If you can lift the concept of machineness, and if you can lift the concept of the time, you can do things like, for example, inside of Docker, they give you like 1 second resolution as opposed to nanotime or the millisecond times. The time shouldn't matter anymore. We can just use, like, let's say you use time to detect that some files were changed, then you can immediately call like SHA-1 hash or something. And then you can think of it as function, basically. And this has a pretty interesting implications. There's a whole bunch of build tools out there. I think the Bazel is one of the first ones that implemented global level caching across the organization. So if you don't have to compile, like your colleague has already compiled that particular source, you don't have to do it anymore. You can just grab it. The other kind of interesting aspect is the compiler integration. So what does that mean? Thus far, like I said, Zinc has been sort of like an afterthought or add-on to the compiler. But we can treat incremental compilation as a first-class feature of the compiler itself. So we can test for a specific bridge as opposed to downloading jars and hoping it works. Or we can evolve the bridge together with the language spec changes, because there's probably a whole bunch of lags right now because it's not maintained by the same people. Or like when we send a pull request to compiler, you're not checking for the compiler bridge aspect, right? Dottie already is starting to go to this direction because they implement their own bridge. But I think there's a whole bunch of stuff we have to do to make sure it actually works. one of the kind of interesting ideas I think many people have like presented is that phase, what I mentioned, the API extraction, right, in order to do the name hashing. Compiler knows this stuff, right? That's what Pickle basically is, right? Pickle is able to do separate compilation. That has enough information to do that. So in other words, we might be able to basically merge these things together so that the Pickle is the information that's being used for incremental compilation. And that basically you can get rid of that whole phase. And that will basically save memory because we don't have to duplicate the whole type information. That gets pretty big inside of your memory when you're doing compilation. The other interesting aspect of using the pickle is that the pickle is already in a jar of stuff that's in Maven Central. So that means we may be able to actually expand the concept of incremental out into not just your subproject, but potentially to other stuff like Cat's Core or Akka or whatever you just randomly download from the internet. You might be able to resume compilation from there instead of basically, oh, your library changed, so we have to do full compilation. This is also mentioned by Lori already, but because we need the signature, right, to do the incremental compilation, outlying types is a really, really interesting concept, right? Outlying type basically says instead of type checking the entire stuff, like I said, it takes 50% of your compilation time, we can just look at your source code potentially and just skim through just the return types of your method. It's much, much faster than looking at every single if statement and pattern matching and all that stuff. All you need is your return types. If we can do that, and this is actually ongoing effort already, we can pipeline things in massively parallel ways. Because you can basically skip majority of the compilation, the typing thing, in order to pass so in this particular case, right, these like 3 different bars represent different subprojects. So today, what's happening is that, let's say you have like Akka Actor and then Akka Streams or something like that. Everyone is waiting on this one subproject to compile before you can start to hand this off. But if only thing you need is the outline types, we can hand off the compilation of the downstream modules immediately afterwards. And that can basically parallelize a lot of the things. That's pretty much what I have. So if you have questions, please ask on the Slido.
Thank you very much for sharing your knowledge with us. Yeah, so about the questions. There's a question, what does your presentation background show?
Yes, that is actually Zinc Mine Museum in Norway, if you just Google Zinc Mine Museum. So it's, I think, an abandoned zinc mine, and someone made a museum out of it.
Okay, thank you. So the second question is, what's the cause of storing signatures in class files in terms of class loading speed or file size? Is it a good idea to remove this data for production environment?
What's the cost of storing signatures in class files? The pickles? I'm not really sure, like in terms of the size, but you kind of need that for all sorts of things, I think. I'm not 100% sure what, so yeah. Yeah, that's actually a kind of interesting question. I'm not 100% sure, actually. If you don't have to do separate compilation, you might not need it during the runtime, right? So, but at the same time, when you're doing pattern matching, there are certain things that's doing a reflection and stuff. So I'm not 100% sure, but it's potentially possible that once you're completely done in the closed world situation, you might be able to get rid of some of these stuff. Okay, so someone said you need pickles for reflections. Yep. So if you want to do runtime reflections, you need pickles. Yep.